This video is for Unit 12, Thermodynamics. The essential questions are: what are the phase changes, and what is a heating curve, and how do you read one? So phase changes, we probably are somewhat familiar with most of these. We're going to start with freezing and melting. It's basically changing between solid, liquids, and gases. So freezing is when we change a liquid into a solid, and we do that by removing heat. That makes it an exothermic reaction. Melting is going to be the opposite. That's going to go from solid to liquid, and so we're going to absorb heat and heat it up to do that, and so that's going to be endothermic because heat has to go into the substance. The heat of fusion is the amount of heat needed to melt 1 gram of a solid, okay? And so you have different heats of fusions for different substances. For water, the heat of fusion is 80 calories per gram, so that's how much it takes for every gram to melt it. Okay, now let's go to the next phase change. We've got evaporation. And that's when we go from a liquid to a gas, and that happens at the surface, okay? It's a little bit different than boiling, and we'll get to that. And that is endothermic because you have to add heat to that. Condensation is when we go from a gas to a liquid, and that's exothermic because we're taking heat away for that. The heat of vaporization is kind of like the heat of fusion, except it's going from 1 gram of liquid to a gas. Okay, and so for example, water's heat of vaporization is 540 calories per gram. Boiling, in contrast to evaporation, is happening throughout the liquid, and that's going from a liquid to a gas at the boiling point. For instance, water's boiling point is 100 degrees Celsius. Okay, and so here, those molecules are moving from the liquid to the gas phase throughout, not just at the surface. Okay, these last two may be the least familiar to you, and that's because they skip that liquid midpoint. So sublimation is when we get a solid going to a gas. That's going to be endothermic. It has to take heat in order to do that. A good example that you might be familiar with is dry ice. Iodine also does this. Deposition is the opposite. Again, it's gas going straight to a solid. That's an exothermic reaction. And there's an example of deposition. The freezing on your car window. So a heating curve for water looks like this. Okay, so it increases in temperature while it's ice till it hits the melting point. And that's going to be ice and water. If you think about it, ice is not instantly water. It takes a little while for all of the ice to melt. Then it travels in temperature from water, from 0 degrees up to water at boiling point, and then it becomes water and steam, and it's a combination as you continue to add heat. And then the steam can increase in temperature from there. So all this is happening when heat is added. It's going from solid to liquid to gas. Okay, so we have just a solid on this first diagonal line. The flat line is going to be a solid and liquid. The next diagonal will be just liquid. We got liquid and gas, and then the next one will be just gas. And all substances are going to look like this. What may change is the temperature at which you have their melting points and boiling points. As we go across, the potential energy is increasing, and as you go back to the left, the potential energy of the molecules are decreasing. The kinetic energy is related to the temp, so what the temperature does, the kinetic energy does. So on the flat lines, the temperature is not increasing, so neither is the temperature. Okay, so here's another phase change graph, and this could be for anything. It doesn't have to be for water because there's no marking on the melting point or the boiling point. So we have solid, and the temperature is increasing, so the kinetic energy increases, but the potential energy stays the same there. Here we have a flat line, so the kinetic energy is not increasing because the temperature is not increasing, but the potential energy does. Okay, and then we're going to repeat. Diagonal line, kinetic energy increases. Flat line, potential energy increases. Diagonal line, kinetic energy increases. Okay, the same is true in the reverse for a cooling curve. It's just starting out hot and cooling down, so it's going diagonally in the other direction. So my diagonal lines, my temperature is dropping, so my kinetic energy is dropping as well. On my flat lines, my potential energy is dropping.